And I want to talk about how we're going to compare distributions. Okay. And so again, it comes back to coming up with a statistic that's going to capture this idea of how we can compare two distributions, because the heart of kind of these simulations are picking the statistic. And so let's do this with a particular example, but let's kind of focus on some terminology. And so when we talk about an empirical distribution of the statistic, so this idea of empirical, in the context of kind of in this course, empirical means simulated, okay? So this is, so in general, empirical is kind of the experimental value. And in this case, the experiments we're running are these simulations. So when I say the empirical distribution of a statistic, I'm referring to the distribution based on our simulation, okay? And so it's the distribution, and then it's going to be all of the observed values of the statistic that from our simulation and how often they appeared, right? That's just our standard histogram. And the idea here is if the number of repetitions in our simulation is large, if we do a large number of simulations, this is going to be a good approximation to the actual probability distribution of the statistic. Okay, and so typically when we kind of validate these models, we're going to ask kind of like a yes or no question. So we're going to have a hypothesis, and we're going to have that based on the data itself. And so we've looked at a couple of examples of this in the past, right? And so, and the idea about running these simulations is going to allow us to kind of decide whether one of the viewpoints is the correct one. And so we're going to formulate these questions such as chocolate has no effect on cardiac disease, right? So that's one view, has no effect. And then the other viewpoint is that yes, it does, right? So it either has no effect or it has some effect. And the example that we looked at last class, this jury panel was selected at random from eligible jurors. Well, we didn't look at whether there was college degrees or not, but you can ask that question. And the other viewpoint is no, it has too many people with college degrees. Okay, and so this comes down to this idea of that we want to compare distributions. And so the example that we'll take a look at comes from this ACLU report from 2010 that looked at, in particular, Alameda County in California. And it looked at the jury panel versus the kind of what the law said versus what kind of actually happened. And so this is a good case to look at because they spent a lot of time collecting data and analyzing it so we can kind of grab their data. And so to kind of understand what they did here, it's helpful to first understand how the jury panels work in Alameda County. And so the idea here is that just by kind of being a resident in a county based on some criteria, you're eligible for jury duty, right? And that's usually required being of a certain age and usually 18 or above and living in that area. And so then from eventually we're going to take from that kind of pool of eligible juries, a jury will be formed, but there's a couple steps in between. And so the eligible jury, right, comes down from a list of eligible residents, and then they get paneled. And so what that means is they're kind of brought in, and then the lawyers get to decide whether they sit on the jury or not, or the judge can disqualify members from the panel from being actually on the jury. Okay, and so Alameda County had or California code basically said that the jury panel, so the thing that we're going to look at is not the jury, because we're going to look at the jury panel, and the law basically said that the people who should sit on a jury panel should be a representative of the population of the area served by the court. Okay, so it should have the jury panel should have the same demographics of the population of that particular county. And so we're going to take a look using the actual data from this study, and see if that actually has happened. All right, and so so basically what they did was, so the ACLU, they looked at actually 11 trials. They looked at 11 federal trials in Alameda County, and they actually kind of, and for those 11 trials, there was 1,453 people across all of the 11 trials were seated for the jury panel. Okay, and so they went and they actually were able to, they went and determined the ethnic breakdown of the people on the panel, and then they used census data to get the ethnic breakdown of the population in general. And so grabbing from that, we have the following tables here. So they broke down their study, kind of just breaking down the population down to Asian, Blacks, Latinos, whites, and then other. And so, and so here we are, we're creating the table. And so the eligible column, this was the actual demographic population level demographics. Okay. And so these were basically the demographic people who were eligible to be on these jury panels. And that basically breaks down to the population. So about 15% Asian, 18% Black, 12% Latino, whites, 54% and other from there. Okay. And so this is the eligible population, and this is what they got across for the distribution across all of these categories, right? And so this is the difference between kind of the example that we're looking at here. So here we have a category, we have multiple different categories in our column, as opposed to the last example we looked at where we just had purple flowers, right? So now we have a bunch of different categories to look at. And so the question we want to ask is so this is what they observed. So the panel column down here, this is what they actually observed across those 11 trials. And so the question we want to answer is, from this source, from this distribution, is, due to random chance, could we get these this distribution of the population across these panels, right? So was the actual thing we observed, the panels, was that due to random chance, or was it some other systematic bias from there? So that's the question that we want to answer. And if we look at it, just kind of eyeballing the data, which is always a good thing to do kind of when we have new data, is just to kind of visualize it to get a sense. You can see that there's definitely some there's some differences here, right? There is some differences across the categories. Whites seem to be fairly represented, but the other distributions, they seem a little off, okay? And so now what we can do is we're going to kind of follow the exact same framework that we have before, where we're going to come up, where we're going to think about what the statistic is going to be, and we'll come back to that in a second. But for right now, I just kind of want to look at the data a little bit from there. And so for this model, right, this is the true distribution of people, and that's we're going to save this at model, and then let's actually, right, run kind of, let's do one experiment. And so now this is kind of, this is the distribution, the population distribution. And so if we ran across 1423, and the reason why we're picking 1423 from there is because that's the actual number of jury members of the jury panel. And so this will give us one simulated result from there. Okay, and that's going to give us the breakdown. And every time we run it, we're going to get slightly different results from there. Okay, but one thing that we can do is that we can just visualize. We can just visualize. So we're not computing any statistics yet on this. We're just kind of visualizing the data. So we've done one chance based on the given source population. And then if we simulate that and create a table here, we can see that, and we can run it a few times, right? To kind of get a sense of, is it jumping around a lot? And if we run it, whoops. We can see, we can see the simulated value that we get, seems kind of in the ballpark of the eligible. And for certain categories, it seems to be a little bit different, right? And if we put all of them together in a bar chart, that kind of shows. So here we have the dark blue is who is eligible to serve on the panels, and who is actually on the panels and are simulated. And you can see, even with just one trial, right? We just we just did one simulation. You can see that they're pretty close to the eligible. There's not a lot of difference between those, but there are, for certain categories, there's certain categories that there's just to be seen a difference. Okay, so I think we're kind of on to something that maybe there's something more than random chance going on here. And so the model that we can construct is that the jury panel was selected at random from the eligible population. Okay, so the distribution that you see the observed distribution of panels was due entirely to chance. Okay, so that is one model that we can have. And then the alternative is, no, they weren't, right? Again, we're kind of give this idea of this hypothesis, either it is or it isn't. And so the model is either going to be valid or it wasn't, right? So it wasn't due to chance, that there was some other forces at play there. Okay, so now we want to come up with a statistic that kind of captures this, right? We had this idea of this distance measurement before, when we started talking about the pea plants, but because now we have multiple categories, we may want to kind of tweak that idea a little bit. And so, I want to introduce this concept of a distance between distributions. And so we're going to look at the people on the panels. They have multiple groups that they belong to. And so another way of saying that is that the ethnicities are categorical. Okay, you can belong not to just you're not either a purple flower or not. You can be one of many categories from there. And so what we need to do is we want to measure the distance between two categorical distributions. And that is the problem that we want to solve. And we want to come up with a statistic that is going to capture that. And please stop if you have any questions along the way. Okay, so again, the question now is that we just don't have two things to compare to, the number purple. We have a bunch of categories where we're doing kind of individual comparisons to. And so we want some notion of how to capture that. And so again, so this is just kind of the same setup before. This is the same table from there. And so now what all I've done here is I've taken the same table that we had on the previous demo, and I just added a column. I just added a column which shows the difference between each specific category from there, right? So I just took our table and then I just added, so I've taken our jury table, added with column, the difference, this diffs. And how did I get the diffs? I just looked at the panels column and I subtracted it from the eligible column, okay? And so this is showing us the difference between the eligible and the actual panels, the panel themselves. Okay, so but again, this is not a statistic, right? So a statistic is some kind of a number that we want to get. And so, but we can kind of look at this difference and maybe kind of give some intuition about how we could come up with a statistic. And the difference is, I think, the start of that, right? Because we can see that this group has a difference. There's a difference here. You know, is there a way that we can somehow capture that? Well, one thing we can do is, like, if we just summarized, if we took the sum of all of the differences. But it turns out that would not work in this case. And why is that? Well, if we look at the sum, you'll see that the sum of the differences is always going to turn out to be 0. And why is it? Because if you think about the distribution of the categories, the way we've kind of defined our set, everyone belongs to one of these following five categories. And so if you took the sum of the eligible column, you'll see that it sums up to 1. Because everyone, you know, so everyone is going to be part of that. And it's the same thing for the panels. The distribution of these panels all sums up to 1. And so if we take this difference, and we can see, we can take the difference, we can take basically the numbers that are smaller, where all of the things that have a negative difference, or they're going to have a positive difference. And if we actually look at them together, if we take the sum of the positive differences, we got 0.11 and 0.13, right? Or 0.03. So that gives us 0.14. And you can see on the negative side, we have 0.1 and then 0.04. So we have -14, right? So if we just took a sum of the difference column, we would get 0. So that's not gonna help us. But what happens if we took the absolute value of the sum? If we took the absolute value of the sum from there, so that would give us a positive number, right? But in some sense, we're trying to measure kind of how far the distribution is, you know, from one way or the other. And we know that because the difference is going to have to sum up to be 0, the difference column has to sum up to 0. We know that the columns that have a negative difference are going to be the same size as the column that has the positive difference. And so that's exactly what we see here, right? On the positive side, we have plus 0.14. And then on the negative side, we have minus 0.14. So if we took the absolute value of the difference, here, let's just actually just do this. And so if we pull off, if we look at the diffs column, right, we can see that's an array. And if we take a sum, if we take the sum of that, we can see we get 0. I mean, it says it's some number, but it's 10 to the -17th. That's just due to kind of floating point rounding errors from there. But the sum is actually different. But if we take the absolute value of that, we can see we got to take the absolute. That is not going to do what I want. What I want is I want the absolute value. So I actually want to pull out these columns. I want to pull out eligible and panel. So E equals, let's see. So we have eligible, right? And then so I just need the P panel from there. So equals jury with this difference. With column. Oops. Oh, sorry, not with column, I just want column. There. And so if we take the absolute, so we get ABS of diffs. So actually, it's just the difference column minus P from there, and if we take the sum of that, we get, yes, of course we get no. What I want, sorry, what I want is the absolute value of each of the individual distances from there. And I'll show you that. I'll show you that in the, I don't want to get too far afield. And so I'll show you that on the next demo. But the point is that if we take the absolute of each difference and take the sum of that, we're going to get 2 times the amount that we want. Because we're going to get the absolute value of the ones that are lower and the ones that it's going to be higher. And so the statistic that we want is actually the absolute value, the sum of the absolute value divided by 2. And that is going to be our total variation difference. And that is the statistic that we're going to use. And so let me show you that. So this is going to be total variation distance. We'll abbreviate that TVD. And so the total area is going to be the difference between each of the categories in the distributions. So we're going to take the absolute value of each difference, and then we're going to take the sum, like I said. And since we've gotten the absolute value, we're going to get twice the distance value. So this is where the dividing by 2 comes from. And I'll show you that here. And hopefully this will make more sense. So this is, again, the same difference panel that we had before. And so this is the, and so we're going to write a function that will compute this statistic for us. This is what I was trying to do in the previous example. And so we're going to take 2 distributions, dist1 and dist2. So this is just a generic function to calculate the total variation distance. Okay. And so this would work with any distribution. Is you pass in the first distribution and the second one. And so again, the statistic that we're going to want to take is we're going to take, remember what we're passing in is we're passing in these distributions, they're arrays, they're columns. And so when we subtract distribution 1 from distribution 2, we're going to do an element by element subtraction. So we're going to take the first element of dist1, the first element of dist2, we're going to subtract the 2 of them together. Then we're going to take the absolute value of that, because we're going to get back in our, so we'll do that and we'll get back from this calculation, we're going to get back a new column, a new array, which is going to be the distance of each individual column. And then there now, because so now since we've taken the absolute value, each column is going to be positive. And we're going to take the sum of that, and then to kind of to get rid of the offset of the fact that we have the same number of positives is the same number of negative differences, we'll divide by 2. Okay, so that now that we have that function, we can now look at our observed data, right? So here we're going to compute the statistic on our observed data. So this is the thing that we actually saw in the real world. This is not our simulation. This is actually what we saw. And so we're passing in the juries, the panels column, right? So that is actually what we saw. And then we're passing in the eligible column from there. And that gives us this statistic of 0.14, okay? And so the statistic on itself is that doesn't necessarily tell us anything until we actually until we run the simulation of, we do our experiment. We run the number of trials and then we look at the histogram, the distribution of the proportion from there. And so that's what we're going to do next. And again, it's going to follow the same framework that we've looked at before. And so we have our function that's going to compute, that computes a single statistic for us, given the distributions. And so now let's look at the statistic of, so here's our observed statistic. And here we're looking at what we would get with one trial of our simulation. This is kind of what we would expect from there. And so again, to keep it with the experiment, we're going to sample proportions, right? So we're going to take a random sample based on our model, and this is the eligible. This is our eligible panel. and we're going to pull, our 1423, and then we're going to compare it. We're going to compute our statistic based on the eligible. Okay, and you can see, so this is the statistic that we observed in the real world. This is our simulated statistic, and we can see if we run it a few times, we can kind of get a sense now that this observed statistic does seem to be a bit of an outlier compared to just kind of a few trial runs of our sample here. But we won't know for sure until we run the experiment and we look at the histogram, and that's what we can do down here. And so here we're just writing a very simple function that will simulate one trial of the experiment, right? And so what we're doing here is now we're running our sample proportions for the same number that was used in the observation, and then computing our TVD statistic on that. Okay, so this is going to be this whole thing here will give us one statistic with the proper number of samples. And then again, here is just our design pattern here. We initialize our accumulator to an empty array. We're going to run this for 10,000 simulations. And so here, instead of just hard coding the number in right here, we gave it a name, and that's a little bit kind of good programming coding style technique. Because one, when you look at this function down here, this for loop, you can see that, oh, okay, this is very clearly the number of times that we want to run our simulation. And if we ever want to change our experiment, the number of simulations, we just change it in one place from there. So that's it's always good to give it a name as opposed to kind of hard coding kind of what is known as magic numbers into your program from there. But the effect of it is that we're going to create our array, we're going to append, we're going to collect our 10,000 results, and now we can actually look at it. We can look at it. And so here we're just setting up our histogram. So here we're just setting up the bins for our histogram, and then we've just taken our column of experimental simulated statistics and turned them into a table. Okay, and if you remember, where did our observed statistics show? If you remember, there was 0.14. Where is 0.14? This is 0.04. So 0.14 is like hanging way, way, way out here. And to really kind of to put that into perspective, and so this is the distribution of things that we would expect to see if, remember what our model was. Our model was that the distribution of jury panels were due to chance. If it were due to chance, and computing this summary statistic of the TVD, this is where we would expect to see. We would expect to see somewhere in the, kind of for most cases, almost all cases, we never see a TVD larger than 0.04. And actually, to actually see that, we can actually just change the bins here. And you can see, where is 0.14? 0.14 is out here, right? And so in this case, it is very, very, very clear. It is very clear that there is something going on other than pure chance with that. All right, before I kind of wrap up for today, is there any questions about that? So this is the statistic, and this is a useful statistic for comparing against distributions. And so what in essence are we doing? What in essence are we doing is we're basically, because we have multiple categories, and we really just want a summary statistic to capture the total distance variation, right? So how much, we're looking at every category in by itself, and we're kind of accumulating those results. We're taking the distance of each individual category that we're comparing to, and we're accumulating the difference. And then we're just dividing by 2 because the total number of things that are going to be greater is the same as the total number, the distance that will be less than. So when we take the sum, so another way of saying this is that we could have done the exact same thing by just looking at the positive differences, right? Because the positive differences are going to be the same as the negative differences. We could have gone through and just calculated only looked at the positive differences, and that would give us our TVD. By taking the sum, by taking the absolute value, by taking the absolute value of the distance and dividing by 2, we're calculating the same thing a little easier. So that's kind of where that comes from. But we're looking at each individual category. We're looking at the difference for each individual category, and then we're taking the distance of that from there. Does that kind of make sense? That's kind of the heart of kind of the statistic and the intuition behind that. I want to make sure that you kind of understand the intuition of that. And so any questions of that before I wrap up? Awesome. Good. All right. So kind of the summary of what we're done here is, and the question we want to ask is that, whether our observed value, could have been just drawn from a randomly, from a sample. And so when we have multiple categories, the statistic we want to use is this TVD, because we're looking at the differences in the individual categories. And the framework, once we have that statistic, we're just going to follow the exact same framework that we did before. We're going to sample at random from the population. We'll compute our statistic, and in this case, it's going to be the TVD. And then we're going to repeat for some large number of times. We'll compare the empirical distribution of simulated, right? So that's what we simulated, the histogram from that, to the actual TVD that we got from the sample in the study. And where it falls on the histogram gives us an indication of how likely that was the actual observed value was due to chance from there. All right. That is, so we have 5 minutes left, and I'm not entirely convinced starting a new topic in 5 minutes is in our best interests. Let me pause.